What's up, everyone? Welcome to Physics with Mr. Simpson. We're going to talk about standing waves today. I'm in my backyard, so you might hear birds and dogs, but you shouldn't hear Max. He's asleep right now. I know that this last topic 4, waves, has been pretty scattered because I haven't really been presenting much. The good news for us is we all have next year to redo things that were done poorly this year because of distance learning. So don't stress if some of the topics here in topic 4 have been confusing and you still have questions. We're going to redo some stuff next school year. And we'll have plenty of time. It's not going to set us back or anything. So don't stress. Whatever you learn the rest of the semester, that's great. We're going to go over it again in August. But standing waves are really interesting, and they have applications in quantum mechanics. They have applications in engineering. It's one of those things in physics that you can go find really dramatic examples of. Like I think we watched that video of that bridge collapsing at some point in class. That was a standing wave set up in the bridge by wind passing by in just the right way. So engineers have to worry about vibration and standing waves, because if they don't, things can collapse. The first thing you should do before we go any further in this video is pause the video and watch the video that I have on the screen right now. I'll have a suggestion pop up in the top right up here somewhere. Watch that and then come back and play the rest of this video. Hey, welcome back. How about Parker in that video, huh? You should look at the comments for that video. Or you know what? Never mind. Don't look at the comments on YouTube. Never do that. So that's the famous demonstration for standing waves. You use a really long spring, slinky like that, and it's pretty easy to set up a few different modes of standing waves. Some people will say modes, some people will say overtones. There's a lot of different words to describe the same thing. When you see those lobes vibrating up and down, like the way he has it right now, when you see one big lobe like this go up and then down and then up and then down, that's the first mode of vibration. That's the fundamental frequency. That's the simplest standing wave you can set up. And so in these diagrams that I'm drawing, the dashed line and the solid line represent the spring or the string at the two different extremes. So at one moment you'll find that it's up here, and then if you wait a bit, you'll find the whole thing has now appeared down here. So the dashed line and the solid line just represent the two extremes. So if we keep drawing the patterns that you see in the video that you just watched, you will see that these lobes that are vibrating up and down, there are more of them. And this is called the spot where it's vibrating the most is called an antinode. Antinode. The reason it's called an antinode is because the spot that's not vibrating at all or moving at all is called a node. So the nodes are spots on the medium where the medium is not moving, and the antinodes are the spots on the medium where it's moving the most. And everything in between doesn't have a name. That's just the medium is going up and down there. But the next pattern that you would see when he started shaking it at twice the frequency of that first one, you would see something like this, where there was a node in the middle. And then at the other extreme, it looked like this dashed line. So if we label these, there's a node there, there's a node there, there's a node there, antinode, antinode. And you can keep doing this for more and more patterns. So the first one had 0 nodes in the middle out here. This one has 1 node in the middle. The next one will, you guessed it, have 2 nodes out here in the middle. And when you draw the dots, it's a little easier to get the pattern right. And you do need to be able to sketch these patterns because there is a formula that you can come up with from drawing these patterns, and I never remember the formulas. I usually have to think about what the patterns look like to get to the formula, and that's the better way to do it. Because there's different end conditions that could be happening. In the video and in this diagram, the ends are both nodes, but you can find standing waves where that's not true. You can find one end is a node and one end is an antinode, or both ends are antinodes. It's a little absurd to think about a string where both ends have antinodes, though, because how would you set that up physically and make it work? Because in the video, these people's hands are fixed in place, so it's kind of forcing it to be nodes at the end. But anyway, the point is, practice sketching these diagrams so that when you need the formula, you can come up with it yourself. The next pattern will have 3 nodes out here in the middle, like this, and so on, so forth. Node, antinode, node, antinode, node, antinode, node. None. You don't really need this many to come up with the formula, but the formula relates the length between the ends, call that L. That length is set whenever you have, like, however far these people are standing apart from each other. That's L. Then they're not moving closer together or moving farther apart. So the length between the two ends of the string are set. That number doesn't change as we go from this pattern to the next pattern to the next pattern. But what does change is seemingly the wavelength of these waves, these standing waves. We haven't talked about how they're created yet, but basically his hands are moving up and down and introducing new wave pulses continuously. And those wave pulses go down to the right and hit Parker's hands, and they reflect and they come back to the left. Well, the waves that have reflected and are moving back to the left experience interference with the next wave that this professor created. So you have a wave coming in and a reflected wave, and when they meet, they interfere with each other. And so a standing wave pattern has regions where there is constructive interference, and it has regions where there is destructive interference, and it has regions in between where there's some interference. It's just not all the way constructive or all the way destructive. Do you think an antinode is a region of constructive or destructive interference? That's right. If you said constructive interference, you got it. Do you think a node is a region of constructive or destructive interference? That's right. If you said destructive interference, then you got it. All right, so the next thing is, imagine these waveforms as waves themselves. How many wavelengths does this top one represent? You could envision it continuing like this. So that would be the full wave if it went all the way out here, but it doesn't do that. So this pattern that exists is really half of a wavelength. So 1/2 of a wavelength equals the length between the two ends. On this next one, that is a full wave pattern. That's one full wavelength. So 1 wavelength equals L. This one, it's a full wavelength plus a half. So 1 1/2 wavelengths equals L. This one, it's 2 wavelengths equals L. There's another way we could write these that would make it a little bit more like a pattern. If I put lambda over 2, and then if I put this one as 2 lambda over 2 equals L, and if I put this one as 3 lambda over 2 equals L, and if I put this one as 4 lambda over 2 equals L, do you see what the pattern is? This number on top right here is increasing as we go from one pattern to the next. So if we call that n, where n is either 1, 2, 3, or 4, we get a pattern. And usually you solve this for lambda, 2L over n, and put a little subscript in there. where n can be 1, 2, 3, 4, ... That's the formula for the wavelength of a standing wave when both ends are fixed in place, which forces the ends to be nodes. And there will be another video showing the other possibilities. One end fixed, one end free, or both ends free.